Welcome to another episode of mineral mining. Today we are going to be looking at the application of iteration numbers and depth resolution in IP data interpretation with some of the field data. I'm making the video based on some of the requests from my subscribers. And today we're going to just run through this, and I'm going to show you um, some of the data we've actually acquired in the field. We're going to use about 3 profiles. This data was acquired over lead zinc field, and the lead zinc field is actually active right now. It actually showed some interesting mineralization which is actually being mined right now. So I think also I'm going to run through this in a couple of minutes, and I'll show you some parts of the equipment too. Also, you have to understand the efficacy of Geomatic GD10. Uh, it's a system that I've used for some time. It's just very robust. Can picture get you the picture of the image. Once it's well actually acquired, you can get a nice data, and you can also get interesting results from this. So today, let's just look at it. Once again, don't always forget to subscribe to our channels. The more you subscribe, the more you get notifications about some other videos we're going to be making. My name is NC Gideon. Okay, let's run through that. I will show you some of it. This is um okay. First of all, we've done some other things that include ground, magnetic, and other interpretation, but we are not focusing on that today. We just want to focus on this profile, using it to explain what we actually done there and what we want to bring out in terms of iterations, in terms of depth resolutions we've actually done there, and also the data acquisition. In short, we can't do this actually without the data acquisition. First of all, I will show you some of um, um, the system, what the system is all about. Um, this data was actually acquired using Geomative system, Geomative GD10 or GD10, GD20, and all that. This system can actually acquire um, IP data, ERT data, and SP data. And not only that, it can also go with a lot of electrodes as much as you can, as far as you have necessary accessories to do that. This is some of the parts that are very sensitive in this system. This system requires this is like your switcher. The more you have your cable, the more you use this switcher. This is actually what actually switches from one electrode to another. And you can see all the parts here. It has non-polarization port, the cables, the steel electrode, and all that it takes. This is the cable, what it looks like. The cable comes in 50 meter. Some previous one comes in 120 per row. So you can keep on joining, and it has some cutouts at an interval of 5 meters. The previous one has some cutout at an interval of about 10 meters. So that is just, you can see the two connecting terminals for the depends on the kind of configuration you are using. If you are using double dipole, you are using a pole, you are using different kind of configuration, but the issue here is that it has these two cutout terminals. Now, one is for your non-polarization port and one is for your steel electrode. So these two can actually, you can see how it's actually connected, So these are the example of the non-polarization port it actually uses. This is the steel electrode that this equipment also uses. So just look at example of how you can actually connect it. But here, what you are looking at here is just the power source. It has a power source that looks like the main board itself, But when you are working if you're actually acquiring an IP data, you don't actually require you require a high power source like a generating source. Usually, we normally use about 4.5 kVA generator. And if you are looking for, if you are doing running resistivity or ART kind of data acquisition, you might not need such high voltage. Okay, you can see this is acquisition of 3D data. The 3D data can actually go in this direction. You can see how it takes. And another way we do it is that most of the time, acquiring digs in the field, because of the nature of the field, it might not be easy for you to run your data this way unless you are working for kind of a geotechnical or foundation data acquisition where you are working within a smaller area or limited area, or where that is actually clear of bushes or encumbrances. It's easier for you to lay your cable in this way and acquire your data exactly in 3D and all that. But we also acquire much data in 3D by actually acquiring in 2D, because if you look at it here, what is just this is just like acquiring data in 2D and having a four profile here. But why this is easier is that this you can run this as a four profile. But if it's 2D, you're going to repeat this into four times, you still get the same result. So that is it. So you can actually do this based on one, what kind of what your target, what the location, so many things you need to put into consideration before you design this configuration this way. So, but what we did is we just acquired data based on you know, on our target. You can see how the screen looks like. At the end of the day, as you're acquiring this data, you can see so the sections on the screen. You can actually plot them and all that, but you might not actually see. It's not actually processed, but you will have an idea of how your data is actually looking at. It's actually good for data quality for some corrections. You can see some spikes on your screen, so you can go back and also correct that. So let me tell you, it's very important that you understand the the essence of good data. You know, um, it's like garbage in, garbage out. You understand? So you need to acquire good data in the sense that when you are applying your iterations or applying some of the damping factors, you know actually what you are applying for. So this is just what I've said. We've covered the equipment, covered the IP profile. So I will go back to the some of the profiles we're talking about. Then we'll talk about the acquisitions and the configurations, the data processing, and all that. So I'm going to use that some of the pseudo sections to bring out this outline on what we are talking about. Okay, if you look at this now, you will see three profile lines. This was actually acquired at about last year, December. Um, if you look at these two lines, they were actually done in such a way that we are targeting something at a particular depth and at a particular location. We've done the other interpretation structures are not actually here, but you can see how we space this. So we can also do this in 3D, can also model this kind of thing in 3D. We can also, but here we just am interested in 2D, and we're interested in we're trying to say sorry, we're trying to look at we model that and try to look at different iterations. What are we getting? We're trying to filter um, some of um, um, some of the IP data, and also we try to resolve some resolutions based on depth. So when you look at your iterations, look at your filtering in terms of your IP data, we'll find out that sometimes high data of IP can mask the other ones, and you might not really see the true distribution of your IP changeability the way they increase it with respect to some different locations, because it's not just having a high IP. High IP most of the time comes as a result of um, noise or some non-connectivity, or some issues can happen within your line of connections, and you find out that you have a high um, IP that might be giving you an interesting anomaly, and you jump to it, and you think that you've actually gotten something. So if you look at this now, what we've done here is we've done this south. This is southwest, northeast. If you look at this, we've done this with about 6 iterations. We've done this with about 6 iterations, and we um, filtered our IP to 800. You understand? And we modeled to 23. Meanwhile, the data was actually acquired more than this. We acquired up to about 60-meter depth. Now, there is something I need you to understand. If your target is less than that, most of the time, start cut off some data. When you cut off some data, you find out that your data at the surface becomes clearer, because if you look at the principle of resistivity, the principle in which this data is actually acquired, there is no argument that you have finer data, refined data at depths shallower than compared to lower depth. You can't compare your data at 100-meter and your data at 10-meter, or 15-meter or 20-meter. So what we've tried to do here is we try to do some certain things. No, we interpreted this data in different stages and all that. So we'll find out that it's clearer and it's better. We first of all tackle shallower depth and see if there are some signatures, because what we're actually looking for can start from 20 meters, can start from 15 meters. So we'll try to see if we have a signature from that than trying to model everything from 0 to 100 meters. You understand? You have to, first of all, you can cut your data into two. Then after that, you can actually go down to, model them together. Now, what we've done here is to divide it into two. We found that so that it actually, we didn't even bother going down. We did most of our interpretation based on it and tested it with trenching and all that. Definitely we got the material. But one thing with the other one is that you might actually miss. You might actually trying to compound the whole data and you find out that you might have issues. So what we did here is to cut it to 23 meters. If you look at here, this is what we did with different iterations. This is one. If you look at here, also, this is iteration three. You know, our iteration number here is three. Iteration number here is about six. Now, if you look at these two things, they are not actually the same thing per se, but actually give you closely. In terms of resistivity, we don't have much issues. You see, give us closely the same image. You understand? Especially if you look at here, you can see a narrow kind of anomaly here that is actually obviously looks like a fracture, and it starts like from at a very shallow depth, just say about 4 or 5 meters. And this, if you look at here, the surface resistivity is very high, showing you lateritic zones or some areas that are actually devoid of, is not actually saturated or unsaturated zones, So here, if you look at here, you find out that there's a fracture here, and the same fracture actually found here. And in terms of the IP processing, you find out the same fracture also occur here. You understand? You can actually see it here. But if you look at here, now let's look at it. If you look at here, see the difference got here. We'll look at here, find out that the IP anomaly here is broad. It's broad. Look at it from about, it's broad to the extent is about 40-meter width. Definitely the mineral we're looking for is not 40-meter. Now, it's clear that this thing is masked within this and this. And there's something again you need to understand when you are interpreting some of the IP data. Now, you need to understand that when you're interpreting IP data, this conductivity, it deals with principle of conductivity and resistivity. Now, if the formation you're actually probing is well saturated, definitely you find out that there will be much conductivity more than the area they actually require to. And again, the current flows in parts where there are much conductivity, and also the minerals you are looking for, most of the time is not actually detecting it directly. It's not actually the chargeability you are getting is not just definitely coming from those, but it's coming from the areas around it because of the suffix. The suffix, when the suffix is more exposed, the clay particles or the shell is actually exposed or saturated. Now, find out that some of the minerals you are looking for have actually dissolved in some of these solutions. And when they have actually dissolved in solutions, now what are you looking at? You find out that the more they dissolve in solution, the more conductivity you get, the very tendency is going to go high. So now, having known this, have this in your mind, you need to understand first of all, what is your target? Is it narrow? Is it like a dike? Is it like a seal? That is one. Now, what depth are you looking at and all that? That's why most of the time you don't use one physical method to actually come to conclusion. But this using IPERT tomography and all that, it's a ground geophysics that is like pinpointing. This is what you can do to actually put a target, especially for the kind of mineralization we have here in this part of the country that is actually narrow lying, and actually fracture fields. So if that is the case, you need to know that. Then if you look at this now, in this, we use three iterations. That's why you need to test different iterations. Most of the time, people tend to use more than more than five, six, seven iterations, eight iterations, and they go in trying to use another damping factors that are actually small. It depends on the method you are using or the application you are using. Now, if you put in noisy data, sometimes everything about your result starts from the data. If you acquire wrong data or acquire noisy data, definitely you are going to interpret rubbish, no matter how good, no matter how the kind of application, the kind of equipment you use. The issue starts from acquiring amount the wrong data. Now, why is it that it seems that the equipment differs and all that? Some equipment are easy to apply, they are easy to use and all that. Now, when you've acquired data that is actually noisy or very noisy, that actually have so much deviation from the real data, definitely you're going to have so much RMS. Your errors will be very high. Not only that, if you are if you know that your data is a bit noisy, you need to know the right damping factor. You need to increase your damping factor, and also your iterations you need to have a lower number of iterations. So, but for me, I think sometimes I try to have about one, two, three, and start looking at them based on my target. So if I've not done this now, I wouldn't be able to pick out this. Now, if you look at this and look at this, you find out that this particular region seems a bit isolated from this. This seems to be masked in this also. And if you look at this also, it's not the same thing here. But if you look at the resistivity did not actually change. But in terms of IP, which is actually if you are looking for areas of changeability, so you need to ensure that this is that. And you can look at low, you can see they will have a very high conductivity and high changeability, which is like low resistivity and high conductivity in this particular location. So you start looking at this particular location. Now, this is a fractured zone. You understand? Now, the fracture zone here actually doesn't actually correspond to high changeability, but this can actually mark or map structures in terms of fractures. So this is what we see here. Then, if you look at this, also this is another profile. If you look at this profile, um, you can see what we see here. And this profile, the same depth, but this is about 4 iterations. This is about 3 iterations. So if you look at this now, look at the one that we use about 3 iterations. You find out that you have a clearer image or clearer picture here, compared to here. Now, in this location, you find out that the resistivity here is very low, but here the IP data here seems to be not very conspicuous and masked. Now, if you look at here, it comes a bit out here as a kind of fracture, another structure that is actually very distinct from this and that. But if you look at this, you start looking at high resistivity. Now, you can't just interpret it without geology. If your geology is more of shale or more of sandstone, then or that is unsaturated, you can be looking at high resistivity here and very high durability for sulfide mineralization or kind of, then if it's something that is you're looking for very low resistivity and very high changeability, look at somewhere here. So this also can also form a target. But here, this one was quite good, but because this was actually um, opened, this particular location was actually opened. Then look at this, the third profile. The third profile, we applied 6 iterations here, and we filtered this down to um, when we get usually when we get high um, IP data, what we try to do is we filter it out and remove high numbers and see the distribution, because most of the time when you are grading, the high numbers will mask a lot of things, so you won't be able to see in details what is there. And that is the sense of depth resolution, trying to resolve from depth to depth. Now, what we've done is we resolve from 0 to 23 meters, first of all. So we were able to see at shallow depth clearer um, signatures and start merging them with what we have down at a very deeper depth. But at this location, we can see. Now, at this particular profile, something was very interesting here. We did some other scanning and did some other methods here. The mineral of interest is actually this particular, and here we're able to actually see a sloping kind of formation. Here, if you look at it, it was a very high here and it slopes this way, and here you can see it slopes a bit this way. I think if you look at this is where we got it clearer. At this particular place, you see what we did? We elevated our IP numbers. We filtered it to about 500, with 5 iterations. And there was a very clearer picture at this particular location. You see, at this particular location. Now we see this actually narrow, a kind of a narrow body, seems to be fracturing between them. But if you look at this is the same kind of body. That was why we are trying to look at this trigonometry around here. What it looks like, where it's actually sloping, and the depth possibly where it takes, because we don't actually know this, you won't be able to look at where you're going to drill, the direction of your drill, or where you're going to, if you're looking for trenches, the kind of the length you'll be looking at for trenches and all that. So the same thing here. See what happened here? We actually try to, okay, cut up to 800. You can see here it is more detailed because we cut to 500. Here we cut to 800, filtered up to 800. Um, you see 500 here, 800 here. You see there's the mask here. There's a mask here in your grading because here we use linear grading and here we use another kind of grading here. And if you look at here, the interesting thing is that we picked there was something that is actually isolating. For this place to be isolating, which actually matches with here. So we think that this particular anomaly becomes, no matter what, even if you are positioning your drilling, you must first of all look at this particular location and all that. Now, one thing apart from this, if you look at all these profiles, you find out that the continuity between 120 and 160 line, you see, between 120 and 160. So if you look at here to this is it, this is it here, here, then that is also this. Now that shows that there is a clear, that where your structures or where your anomalies are running are one, they are consistent, running in the same, running in the same direction, dipping in the same direction, looks like a narrow one. Not all of them actually revealed the behavior. Most of the time you won't actually see this. Now, that is it. Then look at this also. This is the same thing, but if you look at this now, this is what we are saying. We'll now try to do this at a 46-meter depth. Is at 46-meter depth. At 46-meter depth, there are a lot of we are not actually seeing details. It went in to start bringing out some specific points and all that. But still, we still got some, an interesting points here. But it is not as detailed as this. You see, the pattern of resolving your debt from, one level to the other. So I think in this, we're able to, you know, show, summarize the results actually gotten from this. Profile line tree shows some anomalous zones, this to that, along that, and there is a very clear fractal zones between the two anomalous bodies of high turbulence and high conductivity. So in summary, the imaging techniques we are able to do some, you know, we're able to detect some anomalous zones along the profile lines, and the zone of high interest is those that actually correspond with the interpreted structures and have some high changeability and high conductivity or high resistivity. All parameters actually here need to be tested. And when it was actually tested, we try to test, it's not all of them, but we try to test the one that we think that are actually very high, and they showed from positive results. So that is the chargeability body simply dipping up. That is it. It shows the dipping and the striking. Definitely because the striking are easier to determine because they are actually going in the same direction. So at digs, based on digs, there are trenches that we actually recommended. The length of the trench and the minimum depth. This is first easier to do because if you can trench down to each meter, it's easier for you to start seeing some anomalies and in the direction which you are actually asked to do. And also from this, we're able to understand some of the priorities area you want to do first and the other. So what am I trying to say? You must understand the easiest way to go about this, interpreting this is try to look at your number of iterations, try to do it about one, two, three, different, if you're using four, five, three, six, and all that. Most of the time, most of the things are within not exceeding five, between three, four, five, something like that. But it depends on the data, it depends on the cleanliness of the data you've actually acquired. Also, the depth resolution, you can try to, cut it and try to resolve it in different depths. Try to work on the former, on the shallower depth, the middle depth, and maybe you combine all of them together. You'll be able to get interesting results. So with this, I will stop here. In our subsequent videos, will bring you possibly another kind of result we've done using this kind of thing. Thank you and keep watching Mineral Mining and also keep subscribing to our channels. Have a nice